Hello everyone, and thank you for coming. Today I'll be presenting our recent work titled "Reasoning Can Hurt the Inductive Abilities of Large Language Models." Before we begin, let me briefly introduce myself. My name is Haibo, and I am a PhD student at the University of Illinois at Urbana-Champaign, working under the supervision of Professor Haohan Wang. My research focuses on trustworthy large language models with a particular emphasis on safety and robustness. Here's the outline of today's talk. I'll first introduce the background and motivation for our study, then explain how we evaluate inductive reasoning in large language models using four predefined games. We'll analyze the root cases of reasoning failures, and finally, I'll present our intervention strategies to improve chain of thought reasoning, followed by a conclusion. Let's start with the background. Large language models have demonstrated remarkable progress in recent years. Models like GPT-4, Cloud, and Qianwen have shown strong performance across a wide range of tasks, from conversational agents to text generation, question answering, retrieving information, and such tasks like language translation. Many of these capabilities now match or even surpass human performance on standardized benchmarks. For example, GPT-4 has achieved high scores on professional exams, solved complex math problems, and even written functional codes. These achievements show that are already quite powerful, but at the same time, we also see something a bit surprising. Even with all this capability, models still make mistakes, especially when they are asked to reason through problems rather than just retrieve or match patterns. To address this issue, many recent workers have proposed using chain of thought prompting or few-shot COT, where the model is guided to explain its reasoning step by step. In theory, this step-by-step reasoning should help the model reach more reliable conclusions, and in practice, it often does, especially in well-defined domains like math or logic, where the reasoning structure is clear. Inspired by the success of chain of thought prompting, the community began to explore a new class of models called large reasoning models. Unlike traditional LLMs that respond directly to questions, LRMs are designed to think before they answer. They automatically generate intermediate reasoning steps, even without being prompted to do so. The idea is to internalize the reasoning process itself. When given a task, these models go through a self-directive thinking phase and then use that internal chain of reasoning to arrive at a final answer. And indeed, these LRMs have shown very strong performance on a wide range of complex mathematical benchmarks. On datasets like AIME24, models such as GPT-o1, DeepSeek R1, and Qianwen3 consistently outperform non-reasoning LLMs. These benchmarks are challenging. They require multi-step calculations, symbolic reasoning, and careful error handling. And this is exactly where step-by-step thinking provides a clear advantage. But this also leads us to a more fundamental question. Are these LRMs really this good? Let's verify this with a concrete example using a Texas Hold'em game. On your left, you can see our game-based test bed, which includes four games: chess, Texas Hold'em, and dice and blackjack. Each game is initialized with both normal rules, which follow standard gameplay, and special rules, which are intentionally artificial and require inductive reasoning to uncover. In this case, let's focus on Texas Hold'em. We start by defining a special rule such as a hand with five consecutive prime numbers beats three of a kind. These rules are not given to the models. Instead, we simulate a set of game transcripts, like the one shown in the middle. Then we give these transcripts to models like GPT-4o and GPT-3o3 and ask them to infer the rule based on these examples without any internal instructions. The goal is to test whether the model can induce the correct logic through induction. And here's what is surprising. The non-reasoning model, GPT-4o, actually gives us a correct rule, but the reasoning model, GPT-o3, spends time thinking, overanalyze the pattern, and ends up with a wrong explanation and the wrong rule. So apparently, reasoning doesn't always help. Also, sometimes it can make things worse. To understand why this happens, we step back and look at the bigger picture. In this study, we focus on three key research questions. Research question one, how well do LLMs perform on inductive reasoning tasks, and has it improved with reasoning models? Research question two, why does reasoning sometimes fall or even hurt inductive performance? Research question three, how can we guide reasoning to enhance inductive accuracy without model retraining? These three questions form the foundation of our study. And to answer these questions, we designed four diagnostic games with special rules and use them to evaluate inductive reasoning in 8 different large language models, including both reasoning and non-reasoning types. Let's start with our first research question, inductive reasoning evaluation. We evaluate inductive reasoning in LLM, like we said, using 4 game-based attacks, and each task presents models with gameplay transcripts governed by 2 types of rules, normal rules and special rules. The model must infer these rules purely on the observation. We use chess as a detailed example due to its well-defined rules and spatial structure. Normal rules are based on the standard chess movements. We define 6 normal rules here, such as Rule 1, move 1 square in any direction. Rule 2, move in an L-shaped pattern. 2 square in one direction and 1 square perpendicular. Rule 3, move any number of squares diagonally. Rule 4, move exactly 2 squares forward in the direction of increasing row. Rule 5, move any number of squares straight, horizontally or vertically. And rule 6, move exactly 2 squares diagonally. And for special rules are designed to be legal but not obvious, introducing hidden constraints that the model must discover from the movement, such as special one, move in a straight line at any number of squares, then move vertically exactly 2 squares. Special two, first move diagonally any number of squares, then move 2 squares diagonally in direction perpendicular to the first move. Special 3, move exactly 3 squares in one direction and then move down 1 square. Special 4, find the nearest blocking piece and jump to the symmetric position on the other side. Special 5, swap the position with another piece in the target square. And special 6, move in straight line any number of squares and then move 1 square diagonal. In each game instance, we define 8 types of pieces. each assigned one rule, either from a pool of normal rules or special rules. We also randomize the border size, which can range 8 to 15. And we shuffle rules assigned to we shuffle these rule assignments across different games to reduce memorization or overfitting. Importantly, we make sure that each piece appears at least 3 times per episode, so the model has a fair chance to observe the rule in action. Models are never given any rule description. Instead, they show short gameplay transcripts. Here is an example of how the game transcripts look like. And LLMs and LRMs are asked to figure out what rules might be governing the movements. Also, we defend we have the rest of 3 games. The second game is Texas Hold'em. This environment is rich in structure and symbolic variation, which makes it a great test bed for inductive reasoning. We define a mix of normal and special rules. Normal rules follow standard poker hierarchy like 3 of a kind beats 2 pairs, a flush beats a straight, and so on. But special rules induce symbolic abstractions. For example, a hand with 5 consecutive prime numbers beats any 3 of kinds, or a hand with alternating odd or even cards counts and minor hand that beats a straight. The model is shown a set of hands and their winning outcomes without any rule description, and then ask them these LRMs to infer the underlying ranking logic. The third game environment is a dice game. Each round consists of 3 dice rolls, and the model is shown a set of roll outcomes and which ones win. Normal rolls might include a roll between 4 and 10 is a small total. Any triplets beats a pair or a pair beats a single. But the special rule again tests symbolic induction. For example, if the total is a prime number, the row beats any triplet. The key here is model have to identify symbolic features like number theory and parity alternation, even though the data is presented in a pure numeric format. Finally, we have the blackjack environment. This one emphasizes threshold-based reasoning and expansion to familiar rules. Normal rules include 21 wins, go over 21 is a bust, and higher total wins if both are under 21. But special rule introduce structure that breaks expectations, like a hand summing to a prime number always win, or 3 cards straight flush counts a win regardless of a total. Again, models must infer these rules from just a few examples without any instructions, without any formulations, and only see this raw observation from the game transcript. Here, a concrete look at how we extract the game transcript across all 4 games. For each game, we define a consistent set of recorded fields per episode, like board size, move, or rogue outcomes, and a corresponding example entry to show how the data is formatted. Here is an example that we record these movements in a transcript.
Oh,
Here,
sorry, I have a question before you continue. You said that what you do is you feed the model examples of the game, but if
yes.
you are making up new chess pieces or new blackjack pieces and you are giving them new powers, how do you simulate their behavior? Do you just randomly generate gameplay?
Yes, randomly generates the gameplay. We make sure each piece will have at least 3 movements.
How do you validate that the movements are fair, as in that the game is not just random, right? Like, for example, in chess, there are, I'm not familiar with blackjack, but I'm familiar with chess, right? So there are techniques and strategies. How can you validate that the randomized game simulation that you play follows the human patterns, or that's not something you care about?
We don't care about the human
Or
patterns.
realistic, sorry, I mean realistic gameplay versus randomly generated gameplay. These are different.
Yeah, we randomly generate the gameplay.
Okay, thanks. Sorry, keep going.
Yeah. It's okay. I know maybe a human not play games like we simulate it. We just simulate this our predefined rules. We let we let we let them move. And let's continue. Okay, here are some performance results across four games. Let's focus on the accuracy for models with and without reasoning. Okay, we observed on normal rows, those are very intuitive or surface aligned. Most models get over 90% accuracy. That tells us these models are good at picking up shallow patterns when they are structurally obvious. But when it comes to special rules where patterns are hidden or symbolic, reasoning models actually do worse. Even though these LRMs are supposed to be good at multi-step thinking, they consistently underperform compared to simpler non-reasoning models. This trend shows up across all four domains. So to answer research question one, non-reasoning LLMs consistently outperform reasoning-enabled models on inductive tasks with hidden rules, showing that recent reasoning strategies degrade performance on abstraction beyond surface pattern. Next, we move to the research question two, where we try to understand the root cases of reasoning failures. Uh, To explain why reasoning can fail, we present a theoretical framework that models chain of thought reasoning as a sequence of discrete operations. In three stage, like posing a subtask, solving it, and summarizing the final answer. Each step K is associated with a reasoning state. We define it as the left equation, and the model does not observe the true target directly. Instead, at each reasoning stage K, it receives an indirect evidence vector GK based on its attempted subtask resolution. We assume the evidence signal follows this equation. It includes task alignment notation alpha k, which represents how well the current subtask focus on the relevant latent structure, and answer noise epsilon k. The epsilon k stochastic models stochastic variance in subtask resolution, including token sampling, hallucination, and unstable decoding passes. At each reasoning step, the model updates its internal belief by integrating a new evidence signal, just like this equation. And we further subtracting y star from the both sides. We define the belief error EK equals to MK minus y star to obtain the recursion. So this equation can be the left side one, and this equation can help us to decompose the arrow into three arrow components. The first one is incorrect subtask decomposition. We name it breakdown error, and the breakdown error directly correspond to poor question alignment. Uh, such as the alpha k equals to zero or negative alignment alpha k less than zero. In such scenario, the coefficient 1 minus gamma k alpha k magnifies or maintains the previous error magnitude and preventing error reduction or even causing divergence. The second one is incorrect subtext solving, and even under the optimal question alignment alpha k equals to 1, the inherent answer generation noise epsilon k introduce stochastic variations at each at each reasoning step. The next one is incorrect final answer summarization. We name it summary error. The third class of reasoning error arises from the deciding when to stop the reasoning process and commit to final answer. So we formulate it this way, and we found it the expected error square is usually in with a unique optimized unstar. So it always have a very unique optimal unstar. We empirically validate the theoretical taxonomy, which identifies three primary source of reasoning failures, like we said: incorrect subtask decomposition arising from incorrect subtask decomposition, incorrect subtask solving caused by noise in subtask resolution, and incorrect final answer summarization resulting from the exclusive reasoning steps. We collect reasoning failure traces from white box LRMs and found that solving error dominates across all models and tasks, accounting for over 80% of failure cases. While theoretically modeled as additional noise, these failures often reveal structure and recurring patterns. Based on our analysis of over 100 failed reasoning traces across multiple tasks and models, we identify three observable subtypes in the solving error. The first one is mass overuse. Models incorrectly apply incorrectly apply mathematical operations to symbolic inputs. The next one is over generalization. Models infer rules from limited examples without sufficient validation. And the third one, hallucinated rules. Models introduce unsupported constraints not grounded in the input of observation. We observed that solving error dominant mostly over 80% of failures. Mass overuse is most frequent, especially in symbolic tasks, showing a bias to misapply mathematical reasoning. Breakdown error peak in text hold'em, while summary errors are very rare, which is normally less than 8%. Thus, we can answer research question 2. Reasoning propagates error when subtask decomposition is misaligned or solving introduces noise. Each reasoning step compounds the mistake. Such failures dominant in practice make deeper reasoning harmful unless each step is reliable. Finally, based on everything we analyzed so far, we now move to research question 2, where we want to improve the COT reasoning capabilities. Still using the example as shown in figure C, When the users prompt in a structured way, the reasoning model is able to successfully induce the hidden rules. Uh, Recent work has shown that systematically aligned decompositions improve reliability in multi-step reasoning, like the figure on the left. Uh, so we we want to just breakdown error associated with misaligned subtask formula. So we replace the freedom form reasoning with structured decomposition templates. Each template separates the reasoning into three phases. The first one is identifying relevant entities in the input. Next one is inducing candidates rules based on observed patterns. And the third one is verifying whether new cases satisfy those rules. This design constrains model output to stay within task relevant abstraction and improves alignment between sub-question and the global task objective. The prompt template as shown in this figure, we separate them into three phases. Solving error arise when model introduce stochastic variations. Even under good decomposition, the most frequent subtypes is mass overuse, where model impose numeric operations onto symbolic inputs. So, in order to mitigate this, we follow the left figure's work. It's being recognized as a jailbreak work, but we brought the idea here to guide solving with worked examples, and that can avoid numeric extrapolation. This example anchor model behavior to structurally relevant patterns, reducing variance and discouraging models generalization. Summary error occurs when reasoning continue past the optimal step count unstart. We know that the expectation curve is U-shaped, so it always has optimal reasoning step unstart. So in order to do that, adopt reasoned idea from the efficient reasoning and impose a strict token budget. We set it 100 tokens per instance, and this constraint limits exclusive generation and encourage early commitment to accurate conclusion. Now let's look at some results. Here, we observed that guided chain of thought prompts improves SR1 to SR3 accuracy by 20 to 40% in games like chess and dice, showing that multiple reasoning failures often co-occur. Combined strategies outperform non-reasoning models by improving reasoning structure, not length. Decomposition works best in structurally complex games. Solving guidance help in symbol-heavy ones. Summarization reduce over generation, but combined methods don't always beat the best individual one due to stage interaction limits. Thus, we can answer the research question 3. Inductive performance improves when reasoning is constrained. We achieve consistent gain by enforcing structured decomposition, guiding solution with non-numeric examples, and limiting over-generation through token budgets. Uh, Combined with these interventions, it can finally reduce error amplification across all reasoning phases. After answering these three research questions, we can now summarize our main conclusion. To conclude, we designed 4 diagnostic games with hidden rules to evaluate inductive reasoning in 8 LLMs, including both reasoning-enabled and non-reasoning models. We identified 3 key reason failures types: decomposition, solving, and summarization errors. Finally, we introduced error-guided interventions that adapt COD generation to failure types, improving inductive accuracy without retraining. That's all my presentation today, and thank you for listening.